Good morning, everyone. Any questions from the homework? Please start putting them on bright space so we can start going over them. You can put them on chat or you can just communicate them orally. Please make sure you do them. If you don't do the homework, you're going to be lost very, very soon. So any questions you have? Okay. Right, so I will be going over two problems, and if you have any, you guys will let me know, and I would appreciate your answer as we are working. So I will go over two problems in the book. So problem number one, I will go over it, is number 23 from your homework. Here is the problem. So we have a system x1 plus h x2 equal to 2 and 4x1 plus 8x2 equal to k. So this is a system here with two unknowns, x1 and x2, and h and k are parameters that they can change values. So h and k are given parameters, so they represent number. We call them parameter. Okay. And for some h and k, the system can have no solution at all. We know that because system can be inconsistent. For some h and k, we can have one solution, and for some we have infinite. So the question is, for which value of h and k will the system be inconsistent, and in case it's consistent, when the solution is unique and when it is infinite. So a very typical type of problem that we have to get used to it. So how do we solve this problem? The same way we solve any system right now. We take it and we associate the augmented matrix to it. So the augmented matrix is, remember, x1 are, x2 are the unknown, and h and k are the parameters. So this will be 1, h, and 2, 4, 8, and k. So this is the augmented matrix. And now we solve as regular. We go to the echelon form. So whenever we have parameter, always go to echelon form, not reduced echelon, because the problem will become harder. So we only go to the reduced echelon form and we start solving. Okay, so let us go to the echelon form. So this is my 1. I have to multiply this by -4, add it to row 2, and this is my new row 2. Okay. So this will be equivalent to 1, h, 2, and then -4 plus 4, this is equal to 0. What am I supposed to have down here? What should I have here? H, you treat it as a number, nothing more, nothing less. I have to multiply h by -4, so this would give me minus 4h plus 8. So you treat it as a number, would leave me with that. And here I multiply 2 by 4, so it's going to give me -8 plus k. So this is a 1, and this is something, -4h plus 8. So this is in echelon form. And as I said, when we are discussing the existence of a solution and we have parameter, we stop at the echelon form. And now I will go back to you, and I'm expecting answers from you. When is the system for which value of h and k the system is inconsistent, and why? Okay, now the inconsistency. Okay, what did you guys do? What kind of answer did you get? Remember, even if I'm not in class, I'm expecting you to do the homework. Crucial. Okay, when is the system inconsistent? It means which h and k make the original system no value. Okay, Addison is telling me when h is 2 and k is not 8. Okay, absolutely correct. Inconsistent, basically, we need a row inconsistent when we have a row of the 4. So basically, if we have a pivot in the last column, it means we have a pivot here, or a row of the form 0, 0, B if you want, where B is non-zero. So that's when we have inconsistency. And this would occur when minus 4h plus 8 equal to 0. And so we want this to be 0, but this to be non-zero. Minus 8 plus k different from 0. This will cause a pivot right here in the rightmost column, hence, so this will give me h equal to 2 and k different from it. Absolutely correct. Now B. For which value of k we have a unique solution. Okay, back to you again. I want the answer and the justification for it. Remember what caused uniqueness in the solution. What caused the solution to be unique? What should happen? Any value when h is not 2. Okay, so your classmate is telling me we have unique solution. So that's his answer. And then we have to analyze it. H different from 2. And I imagine he meant k any value. Is he correct? What do you think? Georgia, can you tell us why? Can you unmute and tell us why, if possible? If not, tell me no, you can't.
If h is equal to 2, then the left side is like the second column is equal to 0. So if h is not 2, then that it won't be 0, which means the system can't be inconsistent.
But why unique?
Oh, I don't have an answer for that one. Sorry.
Okay. Yeah. That's why I want you guys to understand. So anybody else, why your classmate told me if H is different from 2, his answer is correct. The solution is unique, but I want a reason for it. What guaranteed the uniqueness of the solution?
The second variable is defined. So it can't be more than one number if you put in 2. Or if you put in any other number but 2.
All right, what did we call that? Let us use the language we developed last time. What should we avoid? Let me ask the question the following. When do we have infinitely many solutions? Yeah. Rodrigo is correct. When do we have infinitely many solutions? To have infinitely many solutions, it means we need a free variable. And what causes a free variable? We have a free variable when one of the columns that correspond to the variables have no leading. So to guarantee uniqueness, every column that correspond to the variable, it means column 1 and column 2 should have a leading. Otherwise, you will have infinitely many. The column that correspond to x1 has a leading, which is 1. The column that correspond to x2 since there is an H, may or may not have a leading right here. So to guarantee the leading, I need this to be different from 0. Otherwise, if this is 0, we may have a free variable. Okay, so solution is unique when there is no free variable. We have to avoid the free variable. And of course, system consistent. So we have to have both. So we don't have free variable and system is consistent. It means that every column except the last one should have a leading. Okay, I read. Every column except the last one should have a leading. And this will occur when minus 4h plus 8 is different from 0. So in this case, this column has a leading, this column has a leading, and this will also guarantee, and this condition guarantee that the last column has no leading. It means it guarantees the consistency. Hence, consistency. I will read again what I said and I will explain it so you understand the picture fully. Okay, so let me repeat one comment. The problems are from the book. The problems are not on my lab. So you open the book and do the problem that I've assigned on Brightspace. I do not use my lab. Okay, so unique solution, we have to guarantee that we have a leading in every column of the coefficient matrix, and there is no leading here because we want consistency. So for this to occur, this has to be non-zero. But if this is non-zero, automatically I don't care about this one because I cannot have a leading here. So if this is non-zero, we do have consistency and the solution is immediately unique. Questions? Now, finally, C. When is a solution infinite? So C is, when do we have infinitely many solutions? I want the answer and the justification for it. When is the solution infinite? First, what caused the system to have infinitely many solutions? You have to remember what causes to have many solutions, and you have to make sure the system is consistent. Free variable, very good. So how can we have free variable? Whenever there is a free variable, how can we have a free variable in this situation? Question number 1, can x1 be free? Can x1 be free? No, because the leading is 1 here. So this cannot be a free variable. Now, let's look at the column that corresponds to x2. Can x2 be free? X2 be free is depend whether we have a leading here or we don't have a leading. So x2 will be free if there is no leading here. So for this will occur when, so infinite is we have free variable and we have to guarantee that the system consistent. Okay. Okay, so what guarantee the free variable? To have a free variable, no leading in column 2. The only way we can have no leading in column 2 is that minus 4h plus 8 is what? this has to be equal to 0. This is definitely guaranteed that we have a free variable. But this is also another problem. If this is 0, this is 0, this is 0, I have also to make sure that this is 0, otherwise the system will be inconsistent. So we need this is 0, and to guarantee the consistency of the problem, I need -8 plus k equal to 0. So the first one guarantee that x2 is free, and this one guarantee that the system is consistent. So we put those two together. This will give me h has to be 2, and k has to be 8. And it's in this scenario where we have free variable and we will have infinitely many solutions. Okay. So it's infinitely many solutions. Yes, we need both conditions. First one, it gives me x2 free variable. The second guarantee the consistency, because if this is not 0, I will have inconsistency in the system. So I need both conditions for it to be satisfied. Any other questions from that? Okay, this is going to be a recurring type of problem. So please make sure that you go over it and you will understand it. The existence and uniqueness of the solution is a very recurring situation in this course. Any questions before I move on? Okay. Two more questions I would like to discuss before I move to section 1.3. I would like to discuss number 35 with you from the book, number 35. Okay, I will try to put it in front of us, and then let's see, and I will read it carefully so you guys can read. Okay, 35 tells me the following. Suppose you have a 3 by 5 coefficient matrix for a system, has 3 pivot columns. Is the system consistent? Why or why not? So I will read the problem one more time, and then I will expect a discussion. So the question is, you have 3 by 5, so you have a system. The coefficient matrix, 3 by 5 coefficient matrix, has 3 leading or 3 pivot. 3 pivot column. Because when you reduce it, you have 3 leading. And the question is the system consistent? Yeah. Is the system consistent? Okay. Yes, no, what do you say? So first let me explain, what do they mean the coefficient matrix had 3 pivots? Let me explain this very clearly. It means you take the augmented matrix of the system. So the augmented matrix basically is like this. You have the constant term here, constant term, and part here is the coefficient matrix. Understood? That's what the augmented matrix. The first part only have the coefficient of the variable, and this is have the constant term of the equation. Now, when I tell you a 3 by 5 coefficient matrix has 3 pivots, it means when you take this one and you reduce it right here, this piece from here, there will be 3 pivots. It means you will have a 3 leading in this piece. So this will have 3 pivot or 3 leading. And the augmented matrix is reduced to something. Now, 3 by 5 coefficient, it means this part of the matrix is 3 by 5. So the augmented is going to be 3 by 6. So the augmented is 3 by 6 matrix. So the way it is, we have 1, 2, 3. That's the picture. 1, 2, 3, 4, 5. And that's the augmented. So here we have 3 equations and 5 unknowns. That's what they mean by this problem. Okay, now that I explained the situation, my question to you is the system consistent? I expect answer. Yes or no? Yes, yes, because there will be a leading in each row. There would never be a row that looks absolutely correct. The system has to be consistent because if the coefficient matrix had 3 pivots, it means I will have a pivot in this column in 3 columns. But we know that we cannot have 2 pivots in every row. So if you have 3 pivots, it means there will be 3, every row will have a pivot. So it means that every row, because we cannot have 2 pivots in the same row. So if you have 3 pivots and we have 3 rows, sorry, the coefficient matrix has 3 pivots and 3 rows. It means every row of the coefficient matrix, it means of this one here, of the coefficient matrix has a pivot or a leading, whichever you want to call it. So it means, as your classmate rightfully said, it means there is no row of the form. It means no pivot here. There is no way we can have a leading in the last row because this will have one, we'll have one here, and we will have one here. So it needs no row of the form 0, 0, 0, 0, 1, 2, 3, 4, 5. B with B non-zero because this row is going to have a leading. So the B cannot be equal to 0. Okay. Now, is the solution unique or infinite immediately? The system is consistent. Will the solution be unique or infinite? What can you say? Imagine the system. That's what you have. You have 3 pivots. You have 5 variables. Absolutely. It doesn't have to be x4 and x5. The answer is definitely will have infinitely many solutions because we only 3 pivot. It means 3 variables will be basics and you will have 2 free variables. Will there be x4, x5? Not necessarily. It could be x2 because we can have this scenario. We can have a leading here. We can have a leading here. Okay, so the solution definitely will not be infinite because since we have 3 pivot, it means we have 3 basic variable, not at least, exactly 2 variable will be free, has infinitely many solutions. They could be x2, x3, they could be x3, x4. I actually don't know because we don't know how the matrix looks like. So we can have something like this, 1, 2, 3. We can have 0 here and we can have right there. That could be the system. So we'll have x2 and x4 free. So not necessarily x4 and x5. Okay. All right. Please make sure you do the problem, go over what we did in class. It's crucial to move on in the course. All right, any other questions beside the one I discussed? Very good. So today we're going to move a little bit. So as I said at the beginning of the course, the techniques are done. We know the techniques to solve a system. We know what free variable, we know basic variable, and I hope you guys know it and you review it. Today we're going to start the little bit more abstract part of the course. So at the beginning, the only usually background material I need in the course is a little bit about vectors. And since I'm not sure all of you have seen vectors, so I'm going to start by reminding you vectors. I know a lot of you You've seen physics. A lot of you have seen this stuff. So I'm going to spend 15 minutes just to review vectors with you very, very quickly. And then I go start the new material. So section 1.3, vector equation. So we're going to discuss in this chapter, in this section, sorry, two concepts. The concept of something called linear combination. Hopefully we do that today. And then the idea of a span. Okay. But before being able to do any of this, I have to review a little bit vectors with you. I remember that in physics, in most of your classes, there are two quantities. Some quantities are called scalars. Scalars are just numbers. So we use them to measure weight, volume, mass, stuff like that. And we have another physical quantity vectors, which we use to represent any quantity that have a direction and a magnitude, typically force, velocity, acceleration, and so on. So scalar are just a bunch of numbers. Vectors, we need arrow to represent the direction. If you talk about force, it tells me the direction of the force, and the length of the vector tell me how much is the force. So those two quantities that we always work with. So geometrically, a vector, we represent it like this. We have a point here by an arrow, the direction of it. This point here is called the tail. And this point here, some people call it tip or called a head of the vector. And the length from here to here should represent the magnitude of the vector. It means how large is the vector. Now, whenever we have two vectors, we add them. So adding vectors. Okay. Let us recall a little bit how we add two vectors. So the way I will represent vectors usually, so I will call this, for example, the vector u, and I will put an arrow on it. Now the book does not use arrow, but the book always uses bold letters to represent the vectors, which is hard for me to do. So I will always put an arrow on the top of the vector. So adding vectors. So let us recall, so we have two vectors, a vector u and a vector v. Okay, so what does it mean to add them? I mean, if you have two forces and you add them, you talk about the resultant of those. So two ways. One way is called the tip to tail. It means from the tip of u, you draw another vector parallel to v and equal to it. So basically you draw the vector v again, and you go from the origin right here all the way to here. This is the sum. So this new vector, we can call it w, is what geometrically represent we mean by u plus v. Another way we add two vectors, which is relatively a little bit the same, but we give it another name is, can you guys tell me what's the other one? What's the other way you guys do it? Parallelogram rule. Okay, exactly, the parallelogram method. It means you take the two vectors and you draw the parallelogram with side u and v. So as you realize, we're doing the same, but first you draw the parallelogram. And then you go from the tip, the common tail of both vectors all the way to the top. This is u plus v. So as you realize, it's exactly the same way. We call this tip to tail, and this is parallelogram, but the end point is exactly the same. Which one you use is a matter of choice. Part two is scaling of vectors. So vectors, we add them, we create a new one, and then we scale a vector and we create a new vector. Okay, scaling vector. So if you have a vector u, it's a vector u, and let's see for now be a positive number. So c is a scalar. The minute I put positive, I'm really talking about the scalar here. Then we have the vector c times u. What's the vector c times u? You take the vector u and you scale it by c. So if c is 2, it means you multiply it by 2. So the length here, so you take it and you scale it by 2. So this is c times u. And c is positive here, so you go in the same direction as u. And the length of cu, so you create a new vector. It has a new length, is exactly the constant c times the length of u. Okay. So if you have 2u, that's a u. 2u, it means you start from here, and the length is twice the length of u. Now if c is negative, like minus 2u, so this is my vector u. Minus 2u, it means you go in the opposite direction and c. So you start from here, you go in the opposite direction. That is c times u. Okay, if c is negative. So this is, for example, 2u, right here. Minus 2u, it means if this is u, you go in the opposite direction, right there. This is minus 2u. So you go twice the magnitude of u, but in the opposite direction. Okay. So that's geometrically how we add vectors, and that's geometrically how we scale the vector. Now, part two is, to be able to work with vectors, in math or in physics, we make them algebraic in nature. It means we give them components. So let us talk a little bit about component of vectors in the plane. In the plane. All right. First, an important note. In physics, your vectors, naturally, they start any place in the plane. In this course, and that's important for us, so I'll write it in red. In this course, in linear algebra, all our vectors. So whenever I'm going to draw a vector in this course, which is almost daily, all vectors will have their tail at the origin, what you guys call in 261 position vectors. So in this course, all my vectors are position vectors, have their tail at the origin. Now, I know this is not the case in physics because the tail has to tell you where the force is being put or where the velocity is. But in this course, all our vectors have their tail at the origin. So let us see, what do we mean by component of a vector? So this is the plane. You can call it x1, x2. You can call it xy. I don't really care what we call the plane. And this is a vector. As you realize, I'm drawing it from the origin. Suppose this is my vector. And that's a point P, which is the tip of the vector. And this point will definitely has two coordinate, u1 and u2. Okay, so that's 0 and that's P. So what are the component of the vector OP? So let me take P, a point, u1, u2, the coordinate of the point P are called the component of the vector OP, are called the component. of the vector OP. So what do I mean by that? It means you're going to write the following. OP, the vector OP, is equal to U1 and U2. Okay, here is another comment also. When you guys see vectors in 261 or in physics, the way you write a vector, I don't know, every book does it differently. Sometimes you write the component U1, U2. Sometimes you write the component U1, U2. In this course, when we denote a vector, we usually denote it by a 2 by 1 matrix. And there is a reason for that, because you're going to multiply matrices by vectors, which is coming very soon. But always the notation we use is 2 by 1. So it's just a vector, but we use this notation for it. So nothing different is that we always write it like a 2 by 1 matrix. It means we take a bracket and the vectors, the component come up as a column. So we write it as a column matrix. So for example, let me say that draw the vector to 1. Immediately, I'm writing it in this way. Draw the vector to 1. Since we're insisting that we start at the origin in this course, so it's basically boiling down to draw the point to 1 and then connect it. So we all will draw the exact same thing because we're starting at the origin. So 2, that's it, 2. That's a 1. That's the point to 1. This is the vector to 1. So there is no confusion because we're all starting at the origin. Now, whatever I do in the plane is also, I do it in 3 dimensions. So suppose I say draw the vector simple, 1, 2, 3. The minute I hit 3 dimension, I give easy stuff, easy numbers when I need to draw them. So again, the same thing. I can call this x1, x2, x3, or if you want x, y, z, and then we draw the vector 1. Means we have to go 1 unit here, 2 unit here, so that's a 2, that's a 1, and then I have to go up by 3. Okay, and this is my vector, always from the origin all the way to here. So this is my vector 1, 2, and 3. Okay. Part 2 is when we add two vectors geometrically, what is the component of the sum of two vectors? Okay. Please let me know if I'm fast, so I will slow down. So now the component of the sum of two vectors. Is when you take two vectors, you're creating a third. You have two vectors, you add them, you have a new vector. What are the component of it if we know the component of the other ones? Component of the sum of two vectors. All right, so let's see what the idea is. Suppose I have two vectors u, which is, sorry, u, which is u1, u2. So these are the component of the vector. It means they are the coordinate of the point, the head of the vector. And v is v1, v2. Those are my vectors. And I want their sum, u plus v. It means u1, u2 plus v1, v2. And the question is, what is their sum? So let's go back to the picture and try to see a little bit what's going to be the sum. A lot of you know it, should at least, but let us make sure we all know it. So this is my picture down here. And I have the following vector. So this is U1. So this is U1, U2. Means in my head, this here is U1. In my head, this is U2. That's really what U1, U2 is. And then V1, V2, suppose this is V1, V2. And this is what I am, this is the vector V1, V2. It means the horizontal displacement is V1, the vertical displacement is V2. And now I'm going to add them geometrically the way we added them. So I'm going to take from here a vector which is totally parallel. So this is my V, parallel to that. And I add them. So this is my new vector from here to here. I ended up here. And the question is, what's the component of this vector? So basically what I'm asking is, what's the coordinate here and what's the coordinate here? So that's really what the problem is. And once I find them, I know what to write right there. Okay, so what's the coordinate here? Geometrically, what's the coordinate? Anybody can tell me? So I added them geometrically. I ended up here. That's my new vector. So it is U1 plus V1. Haley, absolutely correct. And let's see why it's that. From here to here, this is U1. Let us think a little bit. How much do we have from here to here? So this is U1. Now how much do we have from here to here? Remember, that's the vector V, which is just being translated, no more, no less. So this is nothing more than this distance here is nothing more than the horizontal displacements of the vector V. So this is exactly V1 right there. So the total here is going to be U1 plus V1. So that's really what the situation is. The same argument go for the Y component. This is U2. V is the translate of that. So this is the same vertical displacement. And this is here V2. So geometrically, this is U2 plus V2. So when you add two vectors, you're obviously creating a new one, but the component of the new one, now I feel comfortable writing that this is the sum of the component. So that's how we add vectors. Now, scaling. Of course, we add vectors and we scale. So part 2 is component of the of a scalar times a vector. So component, I start a new page. Component of a scalar times the vector. Let's realize it's all geometric. So we defined this scalar multiplication geometrically, and now algebraically we can find the component of a scalar times a vector. So we have a vector U, U1, U2. And we're gonna scale it. So we take C times U. It means C times U1, U2. So when we scale a vector, we create a new one. And the question is, what are the components of the new one? So we go back to the geometry, and then we use it to find the component of that. So again, it's simple, and I know most of you know it, if not all of you. So this is my vector U. So this is U1, U2. It means this is U1 here, and this is U2. I take the vector and I scale it. It means I multiply. So the vectors, let's assume C positive for the ease of the presentation. It means I keep the same direction, but I multiply the length by C. So this is CU. It means the length from here to here, the length is C times the length of U. So now the question is, what's the component of this one here? So this point here, what's the component of this point? Or the coordinate of this point? Because the coordinate of this point are the component of the vector CU. And now let us watch carefully. So the question is, what's this here? Right there. Anybody? I mean, you should know it. What this should be? C times U1. Absolutely, because use similarity. This triangle and this triangle. The length of this big side is C times the length of that. By similarity, the length from here to here is C times the length from here to here. So this is nothing more than the similarity of the triangle. So this is C times U1. And the same thing here. The same thing for the other side. So if you multiply this length by C, you're going to multiply the y component, the x component by C, and you multiply the y component by C. So the new vectors will have this component CU1 and CU2. Okay, so this is what the component of the sum and the scalar multiplication. So a very straightforward example. Suppose I take the vector u to be 2, 1, and v to be 1, 4. And the question is, first sketch u minus v, or 2u minus v, and then to find its component. Okay, so let us sketch 2u minus v. So to do that, first I need to sketch u. It's 2, 1. 2, 1. This is my u. And v is 1, 4. 1, 1, 2, 3, 4. This is my vector v. Okay, so this is my v. Now I want 2u minus v. 2u, it means 1u, 2u. That's my 2u minus v. If this is v, minus v is down here. That's the minus v. So we can use a tip to tail if you want. So this is the u, 2u, and I'm gonna add to it minus v. It means I have to go down that much. That's the minus v down here. And my vector, I go from 0 all the way to the end. So this is the vector right here. This is 2u minus v. So 2u, and then I go minus v. Now we have to find its component, and it should match the picture, that's for sure. So 2u minus v is 2 times 2, 1 minus v. Now, that's a scalar times a vector. The way to multiply the scalar by a vector, we multiply each component. 2 times 2, 2 times 1, minus 1, 4. The way we add vectors or subtract them, addition is subtraction, it means we subtract component. 4 minus 1 is 3, 2 minus 4 is minus 2. Somehow it matches this picture. The x component is positive, the y component is negative at least. 3 and minus 2, all right? Okay, so this is a very quick review of vectors. These are the operations on vectors that we actually need in the course. We don't need more than that, much more than that. Part 2, we are going to define now what we call Rn. So algebraic definition definition of Rn. So it's R and N, that's the number. All right, before I talk about that, the book uses the word set a lot, So briefly, in math, what is a set? A set is nothing more, is a collection of objects. It's just a collection of stuff. So a set in math is just a collection of objects. And those objects are called the element of the set. The book doesn't use the word element, but the book used the word set. The element of the set. So set is nothing more than collection of stuff, nothing more than that. So for example, I can say let A be the set of all even numbers. So it's collection of objects. The object here are the even numbers. That's really what A is. So what I mean, so A in my mind consists of, sometimes we put bracket to represent set, 0, 2, plus or minus 2. Those are the even number. Plus or minus 4, plus or minus 6, etc. So that's the collection of that. So 2 is an element of A. It means it's one of those objects. 3 is not an element. Okay, so a set, when I say set, it means collection of stuff. I can say let A be the set of all the students at PNW. So the object are the student. A student at PNW is an element of the set. A student not at PNW is not an element of the set. So that is no more than that. So a set is a collection of objects. So whenever you think of set, or whenever you read the word set, you think of collection of stuff. So this is the word set. Now we are going to define algebraically Rn. So first I'm going to not define, first R. You guys see the word R. And what is R for you? What is R for you? It's the set or the collection of all real numbers. All the real numbers. So R, it means I'm talking about all the scalar, all the real number, 1, 2, square root of 2, a half, minus a half, and so on and so forth. And geometric, so algebraically, R is the numbers. Geometrically, a lot of time we take geometry to understand concept. R we represented by a number line. So the element 1 we represented by this dot, that's 1. 2 we represented by this dot here, minus a half we represented by that, and so on and so forth. So R for us is nothing more than the real numbers. Now, algebraically, so what is R2? So my definition is purely the algebraic definition. R2 is also a collection of objects. What object are R2? R2 is the set of all ordered pair the set of all ordered pair of real number set of all ordered pair of real number that we represent. So we have to way to represent those that we represent by a 2-by-1 matrix. So we write, so it's collection of ordered pairs. So everything in R2 consists of two things, ordered pair of number. How are we going to write those numbers? We write them as a 2-by-1 matrix. So we write U1, U2 for element in R2. Okay, so R2, when you hear R2 algebraically, for now, you just think of ordered pair of number. That's no more, no less. Now, how do we visualize? The same way we visualized R as the number line. So how are we going to visualize R2? Or how are we going to visualize this? This is, as you expect, we take the plane, x1, x2, and we visualize U1, U2 as the following point. To use it as the point. U1, U2 in the plane. Okay, so R2 is nothing more than the collection of ordered pair. That's algebraically. Now we want to visualize U1, U2. We visualize it as this point where the coordinates are U1 and U2. Now, very frequently, whenever I am going to visualize it, I'm going to add arrow. And the reason being is that we're going to talk about sum of two ordered pair. To be able to talk about the sum of two ordered pair, which is going to be like the sum of the two vectors, we need to draw this arrow to be able to represent the sum of two ordered pair. Now, the same token, we're going to talk about R3 and effectively Rn. So we're defining them so I can generalize. R3 is going to be the set of all ordered list of three numbers. Of three numbers. Okay, and then we represent them as a three numbers written as a 3x1 matrix. Okay. So a typical is R2 a point or a vector? R2 is the collection of all the points. The reason we use vectors because we're going to add 2 points. So very soon I'm going to define the addition on R2. To be able to add them, if I see them as point, adding them doesn't really make, it's hard for us. So when we start adding them, we see them as vectors so we can add them correctly. So, but for us, R2 is the set of all the points. So R3 is the set of all ordered list of three numbers written as 3x1 matrix. So element of R2 are going to be written U1, U2, U3. Finally, Rn, pure algebraic, and every vector here, this is going to be represented like this. That's the point, U1, U2, and U3. That's how I represent this point. I draw the vectors when I'm going to add 2 points. Now what's going to be Rn? So my definition so far is purely algebraic. What's going to be Rn? Okay, Rn. No more than that. That's the definition we use. Rn is going to be nothing more than the set of all ordered list of n numbers. Ordered list of n numbers. So written as a n×1 matrix. A typical element of Rn is a list of n numbers. So that's the definition of Rn, is just a list of n numbers written as, and they are called vectors. That's the name we gave those points. So for example, if I tell you fairly easily, give me 3 vectors in R5. Give me 3 vectors in R5. What does it mean? My definition is very algebraic. It means you have to give me 3 lists of 5 numbers. So give me 3 vectors in R5 means this is 1 vectors. R5, it means I need 5 components. So 1, 2, 3, 4, 5. That's it, no more than that. Another one, just give me anything. Square root of 2, 0, minus 1, 4, 2. And so on and so forth. 1, minus 1, 100, 1, 2. So these are vectors in R5. So R5 for us is nothing more than a list of 5 numbers. Okay. All right. Now, so algebraically, that's what R5 is. That's what R2 is. Now we are going to define a addition and scalar multiplication on Rn. So addition and scalar multiplication. And the way we are going to define it is we kind of extend the addition that we just saw on R2. So what do I mean by that? Addition in Rn. So suppose we have 2 vectors, u in Rn, it means that's a collection. I have n numbers here, and v is another vector. I have n numbers here. Then u plus v is a new vector and is defined in the most intuitive way. Okay. Now, the idea is when mathematicians defined addition on Rn, what they wanted to do is extend our geometric intuition or our geometric understanding of sum of 2 vectors. So the way the addition is exactly the way we added geometrically 2 vectors in Rn. So it's the same thing. So it's going to be u1 plus v1 because we extend the definition, we're not creating something weird. un plus vn. Because geometrically, in R2, if I represent this by a vector, this by a vector, geometrically the sum is obtained by adding the component. And we generalize this idea algebraically. Now scalar multiplication of vectors. Okay. Again, we extend the definition, we extend our intuition from R2 to Rn. So C times U, that's a new vector, is we multiply every component by the scalar. Okay. Now, important note that we defined addition in Rn by adding 2 components. We cannot add a vector in R2, it means a vector with 2 components, to a vector in R3. So we only add vectors with the same number of components. So note, we only add vectors with the same number of components. of component. It means the following is nonsense. The following is nonsense. So 1, 2, that's a vector in R2 because this is a list of two numbers plus 1, 2, 3. This is absolute nonsense. Okay, so we only add vectors if they have the same number of entries. So this is the review of vectors. So we will talk about Rn, but I don't want you to really worry about it at all. For us, Rn algebraically is just nothing more than a list of numbers. That's really what it is. We define an algebraic structure on it. We define addition and we find scalar multiplication. Now I'm going to start right now by introducing a idea of linear combination today. So here we go. Linear combination. So let us say I give you two vectors, u in R2, 2, 1. And another vector, v, which is -3, 2. Okay. And I'm going to form a new vector. You know, I have those two. So for me, I always actually go here. Now, in the examples I will give, most of the example will be basically R2 or R3 because we can kind of draw them and, you know, understand the geometry. Once I hit R4 and R5, it will be purely algebraic. So this is 2 and 1. That's one of them, and -3, 2. So I'm going to go this way. -3, 2. That's my other. Now, question is, we form a third vector. So we're going to form a vector W as follows. I take U and, for example, I multiply it by U and I add V to it. So that's a new vector obtained from 3 U. So let me sketch this vector. At this stage, U, I visualize it as this point. V, I'm going to visualize it at this point. But when I want to build W, what is W? This is when I start putting my arrow so I can add them geometrically. That's where seeing them as vectors become important. When I'm going to add them, I have to start putting those vectors so I can do them geometrically. 3U, it means that's a U, that's another U, that's a third U. That's 3U. I'm going to add V to it, my V. So from here, I'm going to go add a V. So V should be right there. Almost. So this is my new vector U. This is W. So this is geometrically YW. It means I start with U. Watch what's happening. This is a U. I move a little bit in the direction of U 3 times. And then I turn around and I move in the direction of V. And the resulting is W. This vector W, which is obtained by multiplying U by a scalar and adding V, W is going to be called the linear combination of U and V. And the number 3, the number by how much I stretch U and by how much I stand, are called the weight of the linear combination. With weight, three and 1. It means to get the vector W, I want I stretch the vector u by 3, that's called the weight. And the vector v, I did not stretch it by 1. 1 are called the weight. So formally, what is a linear combination? Now I give you the linear combination definition in a very formal way. The definition will be always given in the most general situation. So definition, I read it slowly. Suppose V1, V2, Vk's are vectors in Rn. So vectors in Rn means this V1 has n component, V2 has n entry, Vk has n entry. Do not be scared with the notation. A linear combination of V1 and Vk is any vector of the form. So what's a linear combination? It's a vector of the form. You take V1, you scale it by C1. You add to it V2 with a scalar put on it, etc. You add Vk with a scalar put on it. C1, C2, Ck are scalars, and they are called the weight of the linear combination. So a linear combination of vectors is nothing more than it's a new vector, which is obtained by taking the vectors v1, v2, vk, and scaling them a little bit. Like we did a minute ago, what we did is exactly, we took u and v, we put a scalar on u, we put a scalar on v, we add them. We created a new vector. This is called the linear combination of u and v. So, for example, suppose I ask you the simple problem. Suppose I take v to be 1, 2, nothing special. V to be -1, 5. And the question is very simple. Give me 3 linear combination of u and v. Linear combination of u and v. Okay. What does this mean? What does it mean? Give me 3 linear combination. Can anybody understand what I'm saying? Can anybody give me one? Okay, I'll explain it. Give me 3 linear combination of v. So one linear combination means you take the vector u, you put a scale on it for u, so you stretch it by 4, for example, and you add 2v to it. This is one linear combination. So here the weights are C1 is 4 if you want, and C2 is 2. Another linear combination, I can put -2u plus 3v. That's another linear combination. It means that there are infinitely many linear combinations of two vectors, infinitely many, and we are going to give them a name actually. So there are a lot of linear combinations. So the weight are -2 and 3. Another linear combination, 4v. What are the weight in this scenario? What's the weight on u and what's the weight on v? What's the weight on u? 0 plus 4v. Okay, so that's what a linear combination of two vectors is. Now the question is, suppose I have a two vectors u and v. And then you don't have to write. And then I have a third vector b, let me call it, I don't know, -6, 7. Suppose I ask you, is b a linear combination of u and v? What do I mean by that? Is b a linear combination? It means that, can you find a weight C1 and a weight C2 such that B could be written as C1U plus C2V? So if I have a vector B and tell you, is it a linear combination? It means I'm telling you, can you stretch U by a little bit and add to it some stretching of V and get the vector B? That's what it means. So let me define this in a more formal way. And next time we will work with those ideas. So let V1 through Vk and B be vectors in Rn. It means each one of those have n component, and I have a lot of them. We say that B is a linear combination of V1 through Vk if we can find weights. So B is a linear combination of those if I can find weight C1, C2 through Ck such that C1, V1 plus etc. Ck, Vk equal to B. It means I can get the vector B by putting weight on those V1 and adding them. That's what a linear combination. So if we can find weight such that B is this, or if this equation B equals C1 V1 plus C2 V2 plus CK Vk equal B has a solution. So B is a linear combination if I can find those weights C1, C2, 3K, such that B could be obtained in this format. So that's what it means for B to be a linear combination. Okay, so since I think I ran out of time, so next time we are going to start working with those ideas, how to show whether a vector is a linear combination or is not a linear combination. And the second thing we're going to talk about is that if you take two vectors, there are infinitely many linear combinations of them. We're going to give them a name, and we are going to call them the span of the two vectors. I stop at this stage. Any questions? Okay, please do the homework. For next time, there will not be a lot because part of the lecture was a review of vectors that the book assumes you know it. But I will assign few problems. Please do the homework. And for those who did not do homework, didn't do the homework for today, please go back and do them. It's absolutely crucial. Okay. Any question before I let you go? And the homework are on Brightspace. They are not on Pearson. It's just on Brightspace. I just use the book. I don't use anything else. You do not say, I do not, wait. Too many questions. Do we have the solution for the homework? I'm trying to assign usually the odd problems where it means the solution is at the end of the book. Okay? And what else? Question? I do not collect the homework. You just do them and ask me in class how to do them. Anything else? All right, so you do them, and next time when I come to class, even though there will not be a lot of them, I expect you to ask me questions. Are you with me? Okay, have a wonderful weekend. Bye-bye, guys.